think I'll finish it Friday. So far, I haven't gotten any of these types of questions from kinetics up on D2L.
Those lab and pre-lab dates at 9.
Not really. I should put due dates on it, but just get to it soon. I haven't been setting due dates because I like to ease into it. Have you finished it? You were going to finish it today?
No, I haven't put it on it.
Oh, you haven't done any of it?
Yeah, I've just seen it.
Anybody else? Anybody not do the lab yet? Okay. Leave it open through Wednesday. Do it by Wednesday. So we'll do another lab Wednesday. I think I might just leave them open Wednesday to Wednesday. So you have time to ask me questions, class and stuff. Since we're not going over any of it pre-lab. Okay. I need to get some of these kinetic questions. You guys, let's start. Let's get started, y'all. I need to get some kinetics questions up for you guys on D2L. Until then, at least look at these examples and make sure you can calculate them the way I did them. I mean for you to have practice on D2L for everything to be on the test. So far, I don't think there's any kinetics up there yet. And I want to go back for a little bit of molality type stuff. But don't worry about that now. I'll go back and go back over it in class. But I'm going to continue with the kinetics chapter, going slow like I did Friday. And we will start today with, I'll only mention here, this is, integrated rate laws. Last time we were talking about rate laws, and that was when we were relating rate like this. There was a K. And it's supposed to be right. So that's where we were last time. Here we were relating rate to concentration. That was rate laws. Integrated rate laws. Concentration to time. Anybody study any calculus? I know I've asked that before. You ever do integration integration and derivatives? Well, the idea is these rate laws, if you find the integral of them, that's the equations we're using today. But that's all I'll say about calculus, just so it frames some of you in. But now we're relating concentration to time. Rate laws. Concentration versus rate. That was last time. This time we do integrated rate laws, which is and again, I'll ask you to not try to do too much with your intuition because the reasons why these equations exist the way they are really well beyond the scope of this class. And let me remind you, first order, second order. Last time we did stuff like rate equals the rate constant times A, B, and maybe this was a 1 and this was a 0, so then we had overall rate was 1, and let me just do a couple more. If we had that, what's the overall rate for that? 2. We could also get a rate to if that was 2. And B was a 0, so we just didn't include it. Okay. If you integrate that, again, I will give you these equations. There tends to be a lot of them in this chapter. Better write. By the way, there's a PowerPoint up with all this in it if you want to try to follow it. If I can get this done soon enough before class, you can download it and print it and bring it and put notes on it. I finished it like 3 hours ago, so maybe you had a chance to. First order integrated rate law. Integrated rate law. And this is where from last time it would look like this. If it's first order, that means we were in a situation like this, where one of them was 0, the other one was 1. So that's how we got overall first, I should say. Overall first order. The integrated rate laws, these are really the same equation, slightly different forms. So same variables, time, the constant, and you have a concentration of A at some time, and concentration of A at time 0 right at the beginning. And it turns out you could also do it this way. I don't really need to pick both of these up, but just let me point out. So you see a negative here and no negative here. The only difference you get there is which one of these you're dividing by. But actually the laws of the natural log, if you swap the numerator and denominator in here, it creates a negative. That would be a review of natural log if I wanted to go into it. But there's those two, and I guess you could also write it this way. Concentration A. One more. I don't know how much time to spend on this, but I can show you how just basic laws of arithmetic, you can get one from one to the other. But I don't mind just giving you all of these on the test so you don't have to figure out how to go from one to another. So we will use this one in a calculation. We'll use this one too. The first order rate law that looks like this. And when I say it looks like this, that means it's based on just one of the two reactants. So I'll start with it's telling you here's a reaction. So this splits out into two of these. There's only one reactant here. So that's why you only see A here. It's necessarily this in this case because there's only one reactant. All right, and you're told, I'm pretty sure I solved these the other day when I was going too fast, but here I am going slower. is telling you the rate constant K is 9.2 times 10 negative 3%. It gives you that, and then it says percent A I would say reactive. So how long for 80% of this has disappeared and gone over here. And it's just this equation. They use this one, so I'll use this one. But it doesn't matter which one of those you use. Since it says 80%, I can just assign 0. Let's say that's 1. I guess that'd be moles per liter, but I'm just going to say that's 1. If it decreases by 80%, what's the new concentration? By fraction.
8 over 10.
What did you say?
8 over 10.
0.8? No, what you're thinking is, this isn't right. I did this over and over practicing for this. You're thinking 0.8. That's what 8 over 10 is. But 80% of A has decomposed. That means the new concentration of A is 0.2. See what I mean? This is decreased by 80%, so what's left here is 0.2. I made that mistake over and over calculating this.
Wait, how did you get 0.2?
If the concentration of this decreases by 80%, what percent is left? 20%. But I'm doing this by fraction. I could say, if this was 100%, and then this decreases by 80%, what's left is 20%. And you could just erase the percent signs. They'd cancel anyway the way this works. And use 20 and 10 if you're happy with that. In fact, let's just do that. So 20% is left out of 100. A with the 0 by it is the initial. And then later, when this is reactive, you have 20% left. And it's just this, natural log. That sets it up. That's really all you need to set it up. Because you're given K, you're given relational facts between the concentrations, and you're solving for the amount of time, how long until 80% is decreased. So the rest of this is plug and chug. This is example 12.6. Use this space over here. And as long as you're okay with using your calculator with logs, it's natural log 20 over 100 equals K, which is, I'm going to write that as 0.00020093. Make it easier to use the calculator. And in my calculator, I'm going to scientific. Here, and I'm going to go 20 divided by 100, and take the natural log, which is here somewhere. I used it the other day, there it is, equals, so I get here, yeah, I got these upside down. This one's the negative one. That's the positive one. Um, 6. T on top is the positive one. Yeah, I had that backwards. Sorry. Off to a slow start. If that's 100 times 0, that's 20. I knew when that negative showed up, I did it wrong. So be careful. That. One hundred divided by 20 equals balance. 1.609. Divide both sides by this. And we should come out in seconds because that's the unit that's there. 1.609 divided by 0.0093. I think we got two significant figures, and that's that. So 170 seconds would be fine. It is going to be seconds, not 1 over seconds. That should be 1. Two significant figures. That's written well in the book. They went ahead and did this as their answer, but these are equal to each other. So whichever one of those I put in the answer for a test would be correct. Okay, so here's one use of the first order integrated rate law. There's a check your learning one you can do here. So in terms of practice for now, since I don't have D2L rolling yet, do that. All right. Now this y equals mx plus b. Y-intercept, y-axis, you've got your slope, and the x value is t. It's like I said before, we're doing time versus concentration now. It's concentration of the only thing that's there, A. This is 1207. Versus time. So I wouldn't wait to practice these. Try to check your learning ones. This one is to those. That's the reaction. And we're going to use this. The question says, this says show the data can be represented by a first order rate law by graphing this, then determine the rate constant for the decomposition. I probably won't have you graphing these yourself on the test, but what you see in the graph, they have the graph there for you to see. Time is down here, and it's not just concentration here, it's the natural log of the concentration. That's the only way you can make this linear. So, concentration, I shouldn't say A, it's H2O2. They're asking you to decide if this is first order by looking at the graph. The graph has, you put numbers here, 0, -1, -2, -3. Okay. This somewhere around here, somewhere around here. 12 seconds there, about here. 15 seconds there, about here. 24 seconds there, down about here. My scale isn't great, but you can look at that and go, okay, I see a straight line. And if I show you a graph that will be straighter than I can draw, that should be straight. So you look at it and you go, it's linear when you graph seconds to, well, this is hours. I should say hours for this one. And the natural log concentration, H2O2. So this tells you, if you graph the natural log is the y-axis versus time, you have y equals mx plus b. So you can look at that and go, yeah, it fits this formula for the first order like this rate. The formula will be different when we go to second order and zero order. So really the fact that it fits this specific configuration for the equation with the natural log there and just time here, the fact that it's linear, you go, okay, it fits this, that means it's first order. And I will draw this for you rather than make you graph it on a test. The way this one's phrased, 12.7, they act like you're going to graph it, but they graph it for you in the answer. The next question is, what is the cadence? What's the negative of the slope? Do you remember rise over run? So that's what we'll do. They use the, you could use the interval between 0 and 6 and the interval between wherever this is and this. But the easiest thing to do is just use the whole thing. Use the interval between the -3 and the 0, and the 0 and the 24. They do give you the data there. So the one for 24, time 24, final, I'll say hours minus initial, which is 0 hours. So this is the run, and I'm going 24 minus 0 for final minus initial. And then I'm going to do whatever this is. And you can look at the data and see it. The natural log, negative 2.772. Put that in parentheses. Minus this is the negative 2.772, and this is 0. So that would be A. Should give you a good estimate of K. 2.772 divided by 24. And those are the digits we're calculating, and I guess I'm good with that because it's 4 digits. They randomly go back to 3. I don't see why. But I won't have this and this on the test, so you're worrying about where the significant figures are. I'll keep it kind of obvious. Again, when you start doing logs, things get weird with significant figures, and we didn't cover that. So in the book it says 0.116. It's first order. And since I dropped all the units out, make sure I use the right equation. The equation for first order x equals 1, then it's liters, x minus 1, and it's moles, liters, 1 minus x. So if you want to put units on K, K equals x minus 1. I feel the need to double check.
How do you know from the graph that it's first order?
First of all, the graph has natural log of H2O2 here, time here. If this particular equation, if it fits this particular linear equation, where this is the y-axis, natural log of H2O2, I wrote it as A, I should have wrote H2O2 here. If it's got that as the y-axis, and it's got K times T, and this is the y-intercept, which is always going to be 0 for these. If it fits this equation as a linear equation, then it's first order. And again, your intuition isn't going to be able to see why this is first order. I'm just telling you, first order, I mean, if you're looking at a list of equations on a page to help you answer questions, you're going to look at first order, integrated rate law, and you look down here, and you go, if it fits that and it's linear, then it's first order.
There's time on the x-axis and L
Yeah, it'll have time here and natural log of this there. And if it's linear, then it's first order. Anybody got that equated from how you do the units? I'm afraid I have that wrong. And I'm going to work backwards to figure it out. So. Yeah, I did it right. 1 minus x. So the units are first order. 1 minus 1 is 0, 1 minus 1 is 0. First order is s to the negative 1. So there's the answer. Whether you did 4 significant figures or 3, don't worry about that. But make sure you can see the units too. I might put on a test. And the only difference is the units. So be able to apply that to decide what the units are. X, this is the order. And this little game is how you decide what the units are for whatever order you are. You remember that? This one has a check your learning on it, and it shows the graph. Again, I won't make you graph this. They show you the graph of the natural log of the time going like that. So what does it tell you if it's not linear? If it's not linear, then it's not first order. Okay, the next one to cover, keep some of this. Let's keep so I'll keep those two, and I'll keep I left something out over there. This did come out negative. there was a negative here, and I just dropped it before I got down here. That's because it's the negative of the slope. So once I saw that negative there, this is what K equals. But it's the negative of the slope that's the actual answer here. So you multiply by -1 and it comes out positive. What's next? So the next thing I'll do, if you look at the PowerPoint I put up, it's got all these equations for you. First order, and now we'll do specifically for this second order. This works for still one reactant that does anything. It's that not that situation. This is overall order 2. This is overall order 2. The equations I'm about to show you are the ones that only go for this type. You with me? Believe it or not, these look a little more simple, even though it's second order. Again, I'm going to give you all these equations just to be able to use them. So there's that, and this is in the form y equals mx plus b. Introduction to first order. We'll do 12.8. Not that. Not that. The reaction they give is six. So it's 2 of these coming together to be 1 of these. Again, there's only one reactant, so it has to be this situation. It can't be this situation. Dimerization, they tell you it's second order. So now you know this equation will apply just from being told that. The rate constant, they tell you (10 to the -2 liters mole per minute. Remind me to turn this back on. It was X minus 1 mole. Okay, it just did it in a different order. They tell you that the initial concentration is C2H6. And since it's the initial, I'm going to put 0 here. Mole per liter. what is the concentration? After 10 dot O. You're just going to use this equation. Not a graph, you can plug and chug for this one. The A0 or the A naught is this value, and this A to the T, or AT, is the concentration after 10 minutes. We're looking for T. I'm looking for this. I would do a little algebra first. Maybe not. No. Let's just calculate the right side first. And I'm going to turn the K into 0.00576 just because it's easier to deal with. Equals K. C2H6. K is 0.200. Going to leave the units off. K is that. T is 10 minutes. 1 over. Get that wrong. This is K. 0.00576 down here is a 0.00 moles per liter. But we're going to come out in moles per liters. So I'm just getting the units out of the way. 10 times this gives me 0.576 plus 1 over 0.200.
Why did you put 1 plus 1?
This
Yeah.
plus 1 over 2.0. That's this. Plus 1 over 2.0 is the initial concentration. You good? All of this kinetics chapter is about plug and chug. Do you have a question?
Yeah. In the textbook, it says that it's 2C4H6.
Oh, yeah.
I didn't know that.
That's actually not going to change anything, but you're right. That's 4.6. I tended to just go, this equals A, and then just write it as A every time, but I'll keep it clear like that. It is C486. All right, what next? 1 divided by 0.2. So that added together is 5.576. 1 over, and let me just say x. We're solving for x. What I would do is invert both sides. So I have x equals 1 over. You guys good with that? Algebra rule, you just invert both sides, and now it's 1 divided by 5.576. So here I get x equals, and I'll keep 3 significant figures just because there's 3 there. There's 3 there. The book probably says they seem to stop at 2 significant figures more often than I would. No, they did 1.79. Good. No, they did 1.79 times 10 to the negative 1. Concentration. This is a concentration. So it's moles per liter. You could also do moles per liter. per liter like that, or you could do the capital M for moles per liter. These are equivalent ways of saying moles per liter.
Why isn't the second here?
Hmm?
Like, don't you subtract one minus, like, 2 from the moles, like the S of the order?
Sorry, what?
Like the stuff above.
This?
Yeah.
It's second order.
So 2 minus 1, so.
We're not calculating, I shouldn't have used the same X, this was order. Maybe that's confusing. We were calculating the concentration. The units that you use that equation for are the units that go on K. Here we were solving for a concentration, so it was necessarily moles per liter. You follow?
Yeah.
Okay. I could keep the units, but really it just makes it way more tedious. With these types of calculations, you always know what your units are. The concentration is always mole per liter. T is always whatever time is mentioned, whether it's minute, hour, or second. In K, well, you use that formula. You can always figure it out. There's a check your learning there you can try. No graph for that. All right, let's see. 12.9. 12.9. I might just sketch this. I think they need to use the same reaction. But they're saying, what if you did this? What if you graphed? They give you some data. They give you time. They give you concentration. And then they give you concentration. They give you 1 over the concentration. They give you, I'm going to say concentration A. This is A. And then they give you the data for each one of these. And then say, okay, use that data to decide whether this is first order. I don't know why I use the same one, but basically what you get is here. So we haven't graphed a second order with this yet. Time. We already know this is second order. It says prove that this is second order by using this data and graphing it. What I would probably do is give you the graphs and ask you whether it's first order, second order, or zero order. If you graph it natural log versus time, you get this. And if you graph it 1 over concentration, natural log of concentration given time, you get a curve like that. If you do 1 over concentration in time, then you get a straight line. Actually, it's not negative. So then you look at equations like this. This one, the y-axis is natural log of A, concentration of A, and you're wanting that to come out linear so that you can call it first order. If it doesn't, then you look at the one that has 1 over concentration of A, and you go, is that one linear? Yes, that one's linear. So that tells you this is second order, because it fits this equation, y equals mx plus b, but not this one, because that's not linear with this equation. So I would probably ask you, here's a graph, here's another graph of the integrated rate laws. And you'll see that it's natural log of concentration over T and 1 over concentration versus T. And the one that's linear, that's the one it's going to be. 1 over A for the vertical axis, that means it's second. That's all right. I don't know how to make kinetics any less sleep inducing. Okay, there's another check you're learning there for 12.9. Have to do that. There. Should put these on just the front of the pages. So now I'm back to 12.8, 12.7, 12.8. So what's missing here is 0 order. Again, I'm going to give you all these equations. You don't even need to memorize them, or even know the calculus it takes to get to them. So this is going to be, when I get to it, it's 1210. 1210 is a 0 order. I'll write the 0 order equation up here. Integrated rate law. That's when rate equals just K, meaning whatever might have been here were zeros. So we just drop it off and it just equals the K. Equation, the integrated rate equation. That's Y equals. Much simplified. They made this one a graphical one. How's all graph? They're referring to, and the symbol for that is W, which is weird. But there's a graph in there. It's just the straight line part that I'm going to graph. And I won't try to put the numbers in this time. So they've got something like this. And they say, so if you have this, a straight line, and you want to estimate K, again, you're doing rise over run. And yes, you have to estimate by looking at this graph, but definitely this first point is 0, and we're in seconds. And definitely this point is 1,000 seconds. This is definitely 0 on the concentration, and this is it's not 1 over A, it's not natural log of A, it's just A, the concentration of A. And then this one, I'll use the estimate they use. That's not 0. Yeah, 0 on time, but it's not 0 here. They estimate this to be around this point. So really, 2, 2, 3. And then they estimate this point to be around. So that point, 0 to 1,000. So we're just doing this.
To estimate
Concentration of NH3, not NH3 on tungsten. But that way you just estimate K. What's 28 minus 15? No, 15 minus 28. So we get this is 1,000. Yeah, that's right. They tell you 0 order. You can also find that out by looking at the concentration on this vertical axis. It's not log, it's not 1 over, it's just the concentration. That tells you it's 0 order. I will write this as 1, 2, 3, 4, 5, 6, 1.3, 10 to the negative 6. If it's 0 order, what are the units? K equals this. Oh, I erased it. So if it's 0 order, x minus 1 is to the negative 1. 0 order. 1 minus is mole. Did I do that right? That's my equation.
Where are you getting these numbers from?
These,
Like
or these?
the
These. 0 at 100. It's rise over run. So this is the run. And you do final minus initial of that. And then the final minus initial here is here to here, but I guess you have to look at the problem and see this axis. They've got it labeled. I just didn't label it. So that's 3.0 times 10 to the negative 3 right here. They've got 2.0 times 10 to the negative 3. And down here they have 1.0 times 10 to the negative 3. So these are estimates based on this scale. But I guess you'd have to look at the problem to see that. And it is an estimate. You just have to do your best. Maybe if I made you do this, I'd give you a little easier access to read. But you got rise up, you got run on the bottom, final minus initial. That's 1,000 minus 0. And then I've got this value, which I figured was 0.0015, and this value, which I figured was 0.0028 just by looking at it. So then I had this minus this. And this ends up being positive because of that negative. The K ends up being positive. K is just always listed as positive. You okay with that? Are you looking at it on there?
Yeah, I'm just like,
Is it reading the scale that's bugging you?
I just don't know what's going on.
Really? Anybody else lost? She's being honest. You're not the only one. This is NH3 on tungsten. Okay. I'm just going to do it again. You're given this graph, and you're given the fact that this is zero order. I could ask you, is this zero order, or is this first order, or is this second order? Do you know how you would tell if you weren't told this? It's linear for one thing. For another thing, what's right here? Is it natural log of concentration? Is it 1 over the concentration, or is it just the concentration? You see it? That's how you know it's first order. Because at A, it's linear. In B, this is what's on the vertical axis. Not this, and not this. So that frames you in. The next question is, what is K? Well, K is going to be the slope over here. Yes, zero order. Sorry. The fact that this is concentration means we're over here where I wrote zero order. And again, I'm going to give you these equations. So you frame in like that, and now you have to solve for K. The K is the slope, as in y equals mx plus b. So now I'm solving for this using rise over run. Rise over run, I could just say delta rise equals slope. In our case, delta concentration of the NH3 over delta time equals K. And that's what I did. I did final minus initial, and final as best I could estimate it, initial as best I could, minus initial as best I could estimate it. And the rest was just crunch the math. And yeah, the final point is to use this formula. I said zero order, didn't I? Yeah, 10 to the negative 1, 1 minus 0, and then just, was this seconds? Yeah, seconds to the negative 1. So you use this little game to find the units. You with me?
So is zero order and first order linear, and then everything above that's
What forces this to be linear is that we did natural log here and natural log here. That'll force a first order to be linear by the graph. If you have this as the natural log of concentration, not concentration, the natural log of concentration, then it will force the graph to be linear. If you have your vertical axis is 1 over this, it'll force it to be linear if it's second order. And if your axis is just the concentration, it'll force it to be linear if it's 0 order. But this is the key. Okay. I could take whatever data that they got for this and go, okay, I'm going to take all those concentrations, and instead of just graphing them, I'm going to take the natural log of those concentrations and the times that go with them, and I'm going to get that. And I'll go, oh, that's not it. It's not linear. I'll go, okay, now I'm going to do 1 over concentration A versus time, and I look at it, I'm still going to get something other than linear. It's not until I do this that I'm going to see linear, and I go, oh, yeah, it's 0. See that? And this is what you do with the data. When chemists do kinetics studies, they get concentration versus time, concentration versus time, concentration versus time over a long series. Then they take that data and they graph it this way, and this way. Whichever one has a straight line, they go, okay, now we know the order with respect to this reaction. One more thing called the half-life. Stop there. At the end of the integrated rate laws, half-life of a reaction. The rest of this, thinking I can finish this on Friday. I figure we'll just start the equilibrium chapter, and we'll stop there for test info. This is called half-life of a reaction. Should have erased that. First order. Two. I suppose I'll skip the algebra. My worry is I think the ACS final gives you a couple of these general equations and you kind of have to derive your way. But, I'll squeeze in how to do that just before the final. Zero order. Keep that equation. Half-life just means meaning if I have A and it becomes B, how much time before I only have half of this left? And that's useful for various things, but let's see. So for first order, if I had this is what I gave you before. I'll skip the derivation. These are actually first order. Okay. So we use the symbol T with the 1/2. Half-life equals the time it takes, and we call that T1 half, or half of the reactant has been used up. And for a first order, and it has this constant in it, I will give you this on the test. So it's that simple for a first order. Half-life for second order, T1 half equals. And 0th order. So all I have left to do for you today is to model these. Just going the wrong way. So this shows a series of data. It shows concentration, that's moles per liter, and 0 seconds. Looks like they go into hours here. And then 0.500 molarity at 2.16 times 10 to the negative 4, 10 to the 4 seconds. And then they let us know that that's 6 hours. And they tell us later the concentration's gone down, and to get to this point, it turns out to be 12 hours. For 18 hours. 0 hours. And all the way out here, we have a concentration That's the data we're getting. Calculate the rate constant for the first order decomposition. Tell us it's first order. All right. So we're using this. So you look over at your equations, you go half-life. Where do they say that? Okay. They don't tell you to use half-life, but you can use it for this. We're going to use all right. Given this definition, what is T1 half? The time it takes for half of the, whatever it is, I didn't even give you the reaction.
6 hours.
Huh?
6 hours.
Say again?
6 hours.
Yes. She said 6 hours. Here we have 1 molar, here we have half of it left. So the time it took was from 0 up to here. I guess we could use hours. They use seconds in their case, so I guess we'll keep seconds. But this is how many seconds it took to cut this in half. You see what I'm saying? So in this case, instead of using the data and graphing it and all that, once they tell us it's first order, and they just want K, we can use the half-life to find the answer. Very simply. Meaning, what do I want to do here? Multiply both sides by that number times 0.693 equals 1 over K. K. See what I've done? And then I'll invert both sides so it equals K. 1 over. And then I'm just going to solve. I'm going to plug in there those seconds. So 2.16 times 10 to the 4 seconds times 0.693 equals K. One, six, 1, 2, 3, 4. So 2, 1, 6 seconds. 1, 2, 3, 4 times 0.693 equals K. First order, 1 minus 1 is 0. 1 minus 1, oh yeah. First order is just that. 21600 times 0.693. I did something wrong with the algebra. All I had to do is multiply both sides by, no I don't. How did they get that divided by that? Yeah, I totally did my algebra wrong. Did y'all see that? Nobody gonna stop me? Did the algebra wrong. I gotta solve this for K. Let me think real hard now. I divide both sides by 0.693. One over K. So now I'm going to do 2.16 times 10 to the 4th over 0.693. That equals 1 over K. 21600 over 0.693. That should equal K. Is that how they did it? Yeah, this is fine. 21600 divided by, it's 1 over K divided by 0.693. That 1 over K. Invert both sides, so now it's 1 over. I'm just keeping a ton of digits. 1 divided by 3, 1, 1, 6, 8, 3. Yeah, probably didn't need to keep all those. End up with I'm going to keep those two significant figures. Maybe I should keep 3. That's 3, that's 3, that's 3. I guess I'll keep it 3. So 3, 2, 1. And the answer is probably going to be in the book 3, 2, 1 times 10 to the 1, 2, 3, 4, 5. K equals that. First order. So they have 3, 2, 1, 10 to the negative 5. Good. So there's a check you're learning that you can practice there. And let me do half-life for this reaction. What is the half-life? So 12.12. What are we told? I guess I went and got the example. Did I? Example 12.8. I just have to look back. Let's look back at 12.8. Go to example 12.8. They tell us it's second order. We're referring back here, and K equals 5.76 times 10 to the negative 2. They've told us it's second order. So we get the K by looking back there. And they say, what is the half-life? So we can figure that out by need also concentration of C4H6 0.200 mole per liter. So I had to look back to 2.8 to get these two data points, and the rest is just using this equation. What is the half-life? So I'm actually solving for the T1 half. 1 over 5.76 times 10 to the negative 2. And that should do it. Second order. That times that. Yeah, set it up right. Just for the sake of my calculator, I'm going to do this again. Zero 5.76 times 0.200, and I get 1 over 1 divided by 0.001152. I didn't get the same thing they did. 10 to the negative 2. I had an extra 0 there. Times 0.2. 1 divided by 0.0115. There we go. It's second order, so it's 2 minus 1, so liters, 1 minus 2. Were we in seconds? So we were in seconds. They referred back one more time to 12.10, which was that first order one. The check your learning one refers back to 12.10. So you can do that one as a 0th order. They tell you it's 0th order. I would encourage you to practice these, because I know it seems like a lot, but since I give you the equations, it's a matter of a little bit of understanding and then applying equations. And concepts like y equals mx plus b. But I'll leave it there. I think I'll finish this Friday. So test. It's not next week, it's next week. Is that right? I think I want to start. No, maybe not. We'll see. But make sure you're following the last two lectures, last Friday and today, to get the kinetics straight in your head. And then we'll be pretty close to ready for test one if we do that. I'll go back for some molality stuff, so that's what I'll do. I won't go to the next chapter.
For the,